Today, we're talking about frames of reference. Hopefully you enjoyed the actual video on frames of reference, and by now you can easily explain frames of reference in terms of a 7th grader could understand. It's just how you're looking at things. Using frames, we're going to just go right to this. Using frames of reference principles, explain why head-on collisions between cars going opposite directions cause much more injury than rear-end collisions. Alright, so for this, it is useful if we draw arrows. That way we can add them together. So let's say we have a car, and that car is going this direction. So here's our car. Call it car A. That's a great car. And then we have car B, who is moving in this direction, but maybe not by as much. So our arrow is a little bit smaller. I think if we were to measure these two, this one would definitely be a little bit bigger, but just to be on the safe side, so that way, so you don't get messed up. There you go. Alright, so if we call this one car A 70 meters per second, and then we call B 60 meters per second. Okay, so 60 meters per second. So if you're in car A, then it appears to you that car B is moving backwards towards you. Because remember, you're going to eventually overtake B, or you're going to crash into car B. So it appears that this is moving 10 meters per second backwards, which is not that great. Obviously, ideally, you don't want to hit anybody, but now that's if you're in car A. B looks like it's going 10 meters per second backwards. If you're in car B, how fast does car A seem to be moving? Car A seems to be moving 10 meters per second towards you. Meanwhile, when you're in the car's frame of reference, there is no movement. Let me give you an example. So, hold on to your lunch. Here we go. When you are moving with me, I'm moving backwards, but if you're looking at just my face, it doesn't appear that I'm moving. You can tell things are moving because of the fixed background behind us, but if it's just you and me and you close off everything else, am I moving? Maybe you can tell, maybe you can't tell. But you shouldn't be able to tell. Meanwhile, if I place the camera in a fixed point, we call this an inertial frame of reference, where the frame of reference is not moving. Now when I'm moving, you can tell that there's definitely me moving around going on. Okay, so the same thing happens to you when you're sitting in a car and you're talking to the driver, or you're talking to somebody else in the back seat. Hopefully you're not taking your eyes off the road when you're driving. Don't do that. Okay? But next time you are in a car, just make eye contact with another passenger. Or if you're sitting in the passenger seat, just stare at the driver's face. They're going to get real uncomfortable. But you'll be able to see that it appears like nothing in the car is moving. Everything's moving relative to the outside, which is fixed, or the ground, which is fixed. Okay, so to car A, car B is moving 10 meters per second backwards. To car B, car A is moving 10 meters per second closer. Okay, so what if car B is not moving? B, because it looks like a bird of some sort. Okay, so if B is not moving, and A is again moving in this direction. This time we're going to slow it down a little bit, and we're just going to say 10 meters per second in this direction. Okay, if you're in car A, how fast is B moving towards you? B is going towards you 10 meters per second in the opposite direction. You're not moving. If you're in car B, car A looks like it's coming 10 meters per second towards you. So it's the same situation for car B as if they were moving 10 meters per second slower. Remember in the first example, this was moving, A was moving 70, B was moving 60 meters per second. Those two situations are completely identical. Okay. Now, so that's in cars moving in the same direction. If we change it up and we look at how things happen in opposite directions, so head-on collision, we have car A moving 70 meters per second to the right, car B moving 60 meters per second to the left. If you're in car A, how fast does it appear car B is going to crash into you? Well, normally we would just take the two arrows, the vectors, and we would just add them together. So we would add this, and then we would add this, and then we're just left over with this because it's being subtracted. So you're left over with the 10 meters per second. But that's not how we have to look at this. Instead, remember that we are adding these two arrows together, but we have one going this direction and we have one going this direction. So what we're actually doing is we're subtracting the second vector, and the second vector is going in the opposite direction. So that means it's a negative. So whenever you subtract a negative, that's the same thing as adding a positive. So we'll see if I can just flip this thing around. Hey, there we go. So now we're adding a positive. So the 70 and the 60 are totaled together to become a much larger vector. Not to scale, but if we add these two together, I think it's clear we're going to get a larger vector. And in fact, that vector is the same thing as going 130 meters per second. So what that means is if you're in car A and car B appears stationary to you, it's the same thing as you hitting car B at 130 meters per second, or 130 miles per hour, whatever. So when you crash into B, it's going to cause obviously a tremendous amount more damage and injury. Meanwhile, if you're in car B, remember when you're in the car, it's as if you're not moving. So you are getting hit with 130 meters per second. So that's the big difference. If you're moving in the same direction, then we already knew that it's not going to be as bad of an injury, but now hopefully you can explain it using vectors.